Now what we've looked at so far when we've looked at logarithms and exponentials, we've looked at all the basic properties to do with them. We've looked at what they actually are, what they mean, we've looked at all the rules and laws of logarithms and how we work with them, and we've looked at very, very basic, simple solving of them. Well, what we need to do is build this up now, and what we're going to look at in this video is solving exponential and logarithmic functions and equations. Now, one very key thing I'm going to say to you before you watch this video: it's vital and important that you are familiar with using the laws of logarithms to help you solve this. If you're not, go back and have a look at that video just now. Look at this one when you've done that, because you need to be totally 100% familiar with them. Now, a logarithmic equation could look something like this. Log to the base a of 13 plus log to the base a of x equals log to the base a of 273 for x is bigger than 0. Now, when we're solving equations normally, we're always looking to have a line at the end that starts the exact same way. X equals. When we're solving a logarithmic equation or an exponential equation, guess what? We still want the exact same thing for our final line. We want whatever the variable is, in this case x, equals to be how our final line starts. Now, when you're solving a logarithmic or an exponential function, there's a couple of key things you need to do. The first thing you need to do is get things on both sides combined. Once you've got that, you're then going to have to start to look at how you can eliminate the logarithm, get rid of that level of complexity that it brings, and then make it as simple an equation as possible to solve. And that's what we're going to look at just now. So imagine I have this: log to the base a of 13 plus log to the base a of x equals log to the base a of 273. Well, I've got two logarithms here being added, and they've both got the same base. So I can use the first rule of logarithms I had, where when I add them, it becomes a product. So what I'm able to say is that log to the base a of 13x equals log to the base a of 273. So I've got log to the base a of something here equals log to the base a of something there. Here's a little cheeky rule for you. If you have log to the base a of x equals log to the base a of y, from here you can easily say that x equals y. You can just eliminate the logs here because they both have log to the same base. That's a vital part. If these are different bases, you can't do that. But if they're the same base, you can just equate the parts that are in here to one another. And we could do the same part here. This is both log to the base a, so I know that this bit equals that bit. So what I'm able to say is 13x equals 273. Now, I'd expect you to be able to solve 13x equals 273. Divide both sides here by 13. When you do that, you get that x equals 21. Look at that, nice straightforward equation to solve once we get rid of the logs, and all we've done to get rid of them is use our rules to combine it all. Here's another example for you then. Up the complexity a touch. Log to the base 11 of 4x plus 3, take away log to the base 11 of 2x minus 3 equals 1. So we've got a constant on this side. This is where it comes into play, the key part I said in the last example of combine everything on one side, combine everything on the other, and then get rid of the logs. So I'm going to use my rule of logarithms on this side to combine everything here. Well, it's this take away that. Remember, that gives us a quotient, i.e. a division. So I'm going to have log to the base 11 of 4x plus 3 over 2x minus 3. That is going to equal 1. That's going to equal that part there. So now, my 11th power of 1 equals this. So what that means is I could take this up here on this side and say that 4x plus 3 over 2x minus 3 equals 11 to the power of 1, which is 11. Because remember, log to the base a of x equals y means that I can write x equals a to the power of y. And that's all I've done here. And now this is a simple equation to solve. 4x plus 3 over 2x minus 3 equals 11. Cross multiply, and you get 4x plus 3 equals 11, bracket 2x minus 3. This kind of equation here, you'd be getting introduced this in S1. I'd expect you to be able to solve this by now. 4x plus 3, multiply at the bracket, 22x minus 33. All the x's on one side, all the constants on the other, and then you just take it from there. What you can then say is fine, so that means 18x equals 36, get it all together, divide both sides by 18, x is equal to 2. Lo and behold, a nice simple solution to that. Great. When we're working with these equations, it really isn't as difficult as you think. Like I say, combine the sides, get them to equal to each other, and then make it a much simpler equation to solve. Same for this sort of thing here. So I've got unknowns this time on both sides of the equation. So I'm going to keep this side here, I'm going to keep this here, combine it, and then see what I can do. So log to the base a of this plus log to the base a of that equals log to the base a of 11p. It's an addition, so it becomes a product. So I know log to the base a of 2p plus 1, 3p minus 10, and remember they're both in the logarithms, so put an extra bracket around them, equals log to the base a of 11p. Now it's log to the base a of something equals log to the base a of something. Think back to the first example. Remember we said log to the base a of x equals log to the base a of y. We were able to just write then that x equals y. We can use that here as well. From that I know that 2p plus 1 bracket 3p minus 10 equals 11p. It's then just a case of getting everything together and solving it. Well, this is going to multiply it to give me a quadratic, so let's do that. So I get 6p squared, take away 20p, plus 3p, minus 10. I'm going to take the 11p over, take away 11p, it's going to equal 0. What I can then do is simplify that down. I get 6p squared, take away 28p, minus 10, equals 0. Now to solve a quadratic, factorise it, and then get our set of answers from there. So factorising the two of those there, what does that give you? Well, first we take out a common factor. So let's take a common factor of 2 out, and I get 3p squared minus 14p minus 5 equals 0. And then factorise this. So we've done a common factor. It's definitely not a difference of two squares, so it's a trinomial. Factorise it using that. And I'm going to get 3p plus 1 p minus 5 in my two brackets equals 0. What I can then do is solve it for both of these. So I've got 3p plus 1 equals 0, or p minus 5 equals 0. I end up here p equals negative a third, and here p equals 5. So we've got two solutions here. However, go back to the question. Up here, it said p is bigger than 4. That was a condition it put on the question when it said it. So of these two solutions, p equals negative a third can't be, because it's less than 4. What I can then say is therefore p has to be bigger than 4, therefore p equals 5. We have to break it down. We have to follow any conditions like this it gives us, but we don't just cross things out. We have to then state why we pick our answer. So here I've stated p is bigger than 4, therefore p has to equal 5. We can't just forego any conditions like that. Now that's nice and straightforward. Everything there so far we've come into contact with has been able to be dealt with rules of logarithms. But what happens if we up the ante and start introducing constants? So let's look at something like this. So I've got log to the base 2 of 7 equals log to the base 2 of x plus 3. And the condition I'm actually going to put in this one is that x is bigger than 0. Now, the issue with this one that it brings up is the plus 3. I can't just straight away deal with that. If I want to combine it all together, I want to get everything on this side in the same logarithm. So I want something in terms of logarithm to the base. Now, remember, log to the base a of a equals 1. And what we're also able to say at this point is that n times log to the base a of a equals log to the base a of a to the power of n. So think of it in terms of this. These are two of the rules that we covered. If I take 3 and I say fine, so if I write 3 as being log to the base 2 of 2 times the 3, so if I just put the log to the base 2 there, that's me use this first rule, but I can then use this second rule to say that that's log to the base 2 of 2 cubed, which is log to the base 2 of 8. If I do that and plug this back in, I get log to the base 2 of 7 plus log to the base equals log to the base 2 of x plus log to the base 2 of 8. I can then use my rules of logarithm to simplify both sides and work it through from there. Well, what that means is I can combine this side here, so I get log to the base 2 of 7 equals log to the base 2 of 8x. And once I've done that, I can then just get rid of the logs. It's the same on both sides. Get rid of them. And then able to say 8x equals 7. Divide it by 8. And I get that x equals 7 over 8. Yes, it required an extra step here in bringing in the other rules that we've covered, but these are all rules that we should know by now. These are all things that we should be able to do in order to solve these things. Okay, we have to be able to do these. So when we're solving logarithmic equations, what we have to be able to do is remember all of these rules. It's vital that we can remember all our laws of logarithms and all our rules when it comes with them. We have to be able to use them, we have to remember them, and we have to be able to implement them at a moment's notice and recognize where we can implement them and what we can implement at any moment in time.